Welcome to the week 5 of our Calculus 2 course. Last week we started talking about improper integrals. This week we will learn how to analyze whether given improper integral converges or diverges using direct comparison test or limit comparison test. Let's review. What makes an integral an improper integral? One of the cases relates to the upper or lower bounds. If either of them or both is infinity, this integral is going to be an improper integral. In case 2, function f of x, the integrand of the improper integral, has infinite discontinuity, either at the lower bound of the integral, at the upper bound, or somewhere inside of the interval of integration. Imagine a case where we have improper integral that is impossible or extremely difficult to integrate. How would we know if the given integral converges or diverges? What if I were to tell you that we don't have to deal with a difficult function f of x? Often we can find a simpler function that we will be able to analyze instead. This is the story behind direct comparison and limit comparison test. Consider function f of x equals to 1 divided by sum x squared plus square root of x. Oh, how I wish we didn't have to deal with that sum in denominator. If instead function f of x I had a simpler function, let's say g of x equals to 1 over x squared, this improper integral from 1 to infinity of 1 over x squared dx would be so much nicer and easier to integrate. We already done it in class, and we know that this integral converges. Alternatively, if instead of integrating function 1 over x squared plus square root of x, I could integrate 1 over square root of x, then that improper integral I would be able to determine as a divergent one. So how do I know if our function f of x behaves more like function g of x or h of x? Let's graph those three functions and compare them. We can see that function f of x, graphed in red, as x increases to infinity, behaves more like a blue curve g of x equals 1 over x squared. This is not surprising. As x goes to infinity, x squared in denominator of f of x explodes and dominates denominator x squared plus square root of x. Something else interesting that we can see. If we look at the values of x, very close to 0, positive, we will see that function f of x actually produces values very similar to the values of the function h of x equals to 1 over square root of x. This is not surprising either. When x approaches 0, x squared goes to 0 much faster than square root of x. So the largest values in denominator of x squared plus square root of x are produced not by x squared, but by square root of x. Let's self-check. Which of the functions would be most comparable to the values of the function f of x equals to x plus 2 divided by 3x to the fourth plus x squared plus x for the large values of x, alternatively for the smaller positive values of x. In case number 1, for the large values of x, in numerator we have x plus 2. X would be definitely producing values larger than 2 when x approaches infinity. So x is the leading term in numerator. If we look into denominator, 3x to the fourth plus x squared plus x, each term explodes to infinity. However, 3x to the fourth goes to infinity considerably faster than either x squared or x. Therefore, 3x to the fourth is the leading term, determining behavior of the denominator. Function f of x produces output values similar to function x divided by 3x to the fourth, which is the same thing as 1 over 3x cubed. Let's find the answer to the second question. Which of the three functions would be most comparable to f of x for the small positive values of x? Well, Let's take a look at the numerator. If x is almost 0, numerator would be slightly above 2. Therefore, 2 is the leading term in numerator when x approaches 0. In denominator we have 3x to the fourth plus x squared plus x, and each of the three terms goes to 0 as x approaches 0 from above. However, x to the fourth goes to the 0 much faster and becomes negligibly small very quickly. Therefore, in denominator, out of the three terms, x is the leading term for the small values of x. We can see that function f of x would produce similar outputs as a function 2 divided by x when x approaches 0 from the right. Determining leading terms for the numerator and denominator of the original function is a very useful skill that we're going to practice more during our lectures this week. See you in class!